about the theory of these things, I kind of go up the ladder, all right, and so forth, all right. So what are some implications here? In fact, I'll get to this later. Yeah. Just as an example. So let's see. If f prime is positive, what does that say about Big Daddy F? Let's say it open interval. It's increasing, all right? Same thing is true for these guys. If this guy's positive, this guy's increasing. This guy's positive, this guy's increasing. Okay, so we have this commonality of relationships. All right. Well, so what? Issue A. All right. So the first derivative, what does the first derivative tell us about how the graph was behaving for a function? It told us where the graph was doing what or what? Yeah, where the function was increasing or decreasing, where the graph is going up or going down. All right. Now, what does the second derivative tell us? It tells us about concavity. All right. Happy face and sad face. Up like a cup, down like a frown. All right. Now, that's Honey's calculus. All right. Y-axis. All right. Okay, so for example, if you take, for example, a parabola like that, okay, the graph here is concave up everywhere. All right. Now, what does that mean? Well, specifically, we refer to the tangent lines. If you look at the tangent lines for this guy, what is always the case here for the tangent lines? The tangent lines are always lying where? Below the graph. Below the graph. All right. So this characterizes being concave up. Okay. Concave up means that the tangent lines are below the graph. Tangent lines are below. Okay. So the graph is curving up away from the tangent line, basically. All right. And for concave up, I'm going to use CU as my designation. All right. So just like I use, positive versus negative for signs, up arrow versus down arrow for increasing, decreasing. Now it's going to be CU and CV, concave up and concave down. And that refers to a graph. Okay, that refers to a graph. These are features of functions. This is a feature of a graph. All right. Likewise. Okay. Well, and in fact, let's stick with this for now. Okay. What are sufficient conditions for the graph to be concave up on, let's say, an open interval? All right. If f double prime is positive, all right. If f double prime is positive, so we need the if there, all right. That implies what? So if f double prime is positive, what does that mean? Look at our relationship here, all right. So remember, it's kind of like a granddad, dad, and you, right? Granddad, dad, and you. Okay. Or someone, son, and grandson, right? Okay. So if my derivative, my son, I was up more, I guess. Okay. So my son, my derivative is positive. What am I doing? If my derivative is positive, what am I doing? I'm increasing, right? When my derivative is positive, I'm increasing, right? Okay. Now, let's say that I'm f prime. I'm not f, I'm f prime. I'm the son now, okay? So I'm f prime. My derivative is f double prime. Well, if my derivative is positive, I am increasing, yeah. So this means f prime is increasing, okay? And you agree that that appears to be the case here, right? So as x increases, right, as x goes to 1, 2, 3, 4, 5, and so forth, what's happening to these slopes, right? Well, maybe this slope is -2, this is -1, this is 0, +1, +2. You agree that the slopes of the tangent lines are increasing as we go from left to right, okay? And that characterizes this concave up behavior. So this implies that the f graph, remember concavity is a feature of graphs, the f graph is concave up. All right. Now one great thing about these relationships is that we have a nice word association that works. Okay, there's a word association that works. If f double prime is positive, that's my grandson, wow. Okay, if my second derivative is positive, then the first derivative is increasing, and my graph is concave up. So positive, increasing up, those words go together, right? So, just psychologically, it's easy to link them together. Right? How to ace calculus likes to draw this picture. Okay, he looks like he's on something. But, up like a cup, concave down. And of course, the graph can change concavity. We're going to call those points inflection points. Now, what happens when a piece of a graph is concave down? All right, so here's an example, x-axis, y-axis. Classic case is a parabola opening downward. All right. Okay, so tangent lines go like this. All right, and notice here, we're looking at a piece of a graph that's concave down, or CD. All right, and the phenomenon here is that the tangent lines are below, or above the graph. Tangent lines are above the graph. Okay, so that tells you when the piece of the graph is concave down. All right. Well, the relationships are analogous to what we have over there. All right. So if f double prime is negative. All right. So let's say I'm f prime. My derivative is f double prime. He's negative. What am I doing? I'm decreasing. So f prime is decreasing. All right? And you can tell that's kind of the case here, right? If you look at slopes, the slope here is 2, let's say, 1, 0, negative 1, negative 2, right? Here, the slopes of the tangent lines are decreasing. That indicates that the graph is concave down, at least here. All right? Okay, so this says that the f graph is concave down. Right? And by the way, this is the link we use more often, the link from here to here. Okay, we don't use this link as often. We more often use the link that when f double prime is positive on an open interval, then the corresponding graph of f is concave up. Likewise here, if the second derivative is negative, okay, the f graph is concave down on that open interval. Right. Again, the word association works. Negative, decreasing, down. The word association still works. All right. So these are easy to remember. They link together. Any questions? Any questions? Right. Okay. By the way, a straight line has, you could say zero concavity. Maybe it's both concave up and concave down, but that's kind of a neutral case. All right. Oh, by the way, what's the picture? Down like a frown. Okay, Harday's calculus. Right, second derivative is negative, then you got concave down. All right. All right. Okay. I hope you didn't feel that way after you got your test. Actually, no, you know, be really frightening. This is the most frightening. That would be most frightening. Okay, that would be kind of okay. All right. Okay. Okay. Now, as I said, if you have now a parabola doesn't have any. A parabola does not change in concavity. Okay, but other guys like cubics, right, or sine, radical sine of x, right? Those guys might change concavity. And they change concavity at inflection points, where you have continuity. All right, inflection points, or points of inflection. All right, IPs, or some books say PIs, points of inflection, whatever. All right, inflection points, IPs. All right, and what are these points? These are points where the F graph changes concavity, meaning from concave up to concave down, or vice versa. So you're going concave up to concave down, or vice versa. All right? And we have continuity. F is continuous. All right. And I won't mess with you in that respect. All right? Okay. Now, before we go on to actually computing these things, let's talk about some practical applications for inflection points. It's not just a matter of graphing things nice and prettily, although that helps, right? So what are some practical applications for these ideas? Okay, well, I'll give you a couple examples in the notes, all right? In my stats class, all right? In my stats class, okay, what's a famous curve in stats class? That's a normal bell, right? This is a normal bell curve. Okay, so that's an example of a normal probability density curve, right? And for a normal distribution, right? So, for example, test scores are often normally distributed, right? Okay. This corresponds corresponds to the, what's the M word here? The mean, mu. All right. And then what's the measure of spread? The SD, which is the standard deviation. All right. Okay. Standard deviation is denoted by lowercase sigma. All right. Now, what is a graphical interpretation for one standard deviation? It's the horizontal distance between the mean line and either of these 2 points. Now remember, this is symmetric about the mean. All right. This is called the inflection point over here. Okay. Why? Because the graph goes from concave down to concave up, right? So the graph is concave down in here, concave up over here. It's concave up over here, right? We also have another IP over here. So in advanced statistics, you would find you'll be given Elevets equals and you can use that to find where these inflection points are, and that graphically defines what one standard deviation is over here. Okay. All right. And about 68% will be within one standard dev, about 95% within 2 standard devs. So almost everyone is within 2 standard devs. Okay. So that's one application, all right, helping to graphically view standard deviations if you're dealing with normal distributions in statistics. Here's another application. All right, population growth. Okay, way back in Math 96, how did you model population growth? Maybe a country grows at 2% a year or something, right? That corresponded to what E word? What kind of growth? E word, exponential. Technically, we haven't seen exponential functions yet. We will in chapter 7. But the old school way of modeling the population, right? Whether it's people or bacteria, whatever. All right. How do you graph exponential growth? It looks like what letter? J. That's like a J curve, right? So that's like a population growth or the spread of a horrible disease or something. All right. All right. We say Justin Bieber fans. What's that? Right. Okay. Who broke up today? Seth MacFarlane broke up with Amelia Clark. I was on Yahoo. Wait, you want to date him? Hey, he makes what? He's worth what? 9 million? I date him. Instead of a J, it might be an S. All right. Okay, it might be an S curve. This is called a logistic curve. All right. Okay. Now, this phase here might be the China phase. Okay. Now, I'm being very broad here. Okay. I don't have the demographics with me, but China population is increasing, but maybe there have been years where, because of the one-child policy, other factors, okay, population might not be growing that fast in the future. By the way, what are some other limiting factors on population? Why might it be an S instead of a J? What are some limiting factors? Resources. Resources? Like what? Food? Water. Water's going to be a big one. Yeah. Water. Place where you can live, right? Arable land. Someone one time said air. I think we're okay with air for now. But water. War. Disease, right? You have disease, right? Because disease can work like this too, right? Okay. What else? Okay, that's the China phase. Now, what country's going to overtake China? Pretty soon. India. India's going to overtake China pretty soon. All right. So what's this point here? This is the point where we go from the India phase to the China phase. So maybe, even with religious issues, maybe once once India reaches a certain phase, they're going to have to start instituting China-like policies, maybe. This is the point, this is the time when, really that's time, right, this is time, right, that's time. This is the time when the population reaches its highest rate of growth, when the population is growing fastest. And then afterwards, not as fast, okay? Guess what? That's what point? That's an inflection point, right? So here is the point where we have the greatest rate of growth, where the population grows fastest, okay? Here it's still growing faster, 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 and then after this point, slower, slower, like a China phase. All right. So there are practical applications for this idea of IP. Remember, derivatives are rates of change, right? And the IP corresponds there to the place where we have the highest rate of change. All right. Okay. Question. Well, any questions? Inflection points. We want to find out where these inflection points are. All right. Well, before we were looking for f prime helped us find what? What kinds of points on the graph? F prime helped us find critical numbers, and that's where we might find what? Local maximum points, right? Now, how do we find IPs? All right. So it's going to be an analogy again. All right. In fact, let's review that. Right. What did we do before? A critical number, right? A CN, a critical number, all right, is a number. It's got to be in what? It's got to be in the what of Big Daddy F. Okay, right? In the domain of Big Daddy F, there has to literally be a point, folks. There has to literally be a point, right? So a CN is a number in the domain of Big Daddy F, all right, where F prime, right, is either what or what? 0, 0, or D&E. So remember, folks, you can have a CN where F prime is D&E, but F itself cannot be D&E. We talked about that with the trig functions and algebraics. Okay. And why do we care? Because CNs are the only places where local, max, and min points, do they have to appear? Anytime we have a CN, do we have to have a max and min point? No. Like y was x cubed? You don't need it, right? But these are the only places where they might show up, where they can appear. Okay, now they don't have to appear. I didn't say must, okay? But the only places where they can appear. Okay. All right. Now, what are we doing now? All right. Now, instead of CNs, and this is kind of my made-up term. It's not that unusual. I'm kind of making this up. But a pin. So I'm defining this by myself. What's a pin? It's a possible inflection number. It did not require great imagination on my part. Okay. A pin. Possible inflection number. Okay. I thought that's appropriate. Okay. So recognize this when I say this. It's a useful tip for you. Okay. A pin. A possible inflection number. Once again, it's got to be a number in the what of Big Daddy F. Okay. Again, there has to literally be a point, right? So it's a number. Okay. Is a number. Once again, in the domain of Big Daddy F. Okay. Not necessarily F prime, by the way, but got to be in the domain of Big Daddy F. Where? Okay. For CNs, we're focusing on F prime. For pins, we're going to focus on who? F double prime. Okay, it's where F double prime this time is what or what? 0 or D. All right. The reason being that we'd like to know where F prime is changing from increasing to decreasing, right? That's what we got here. All right. Now, why do we care about pins? Pins are the only places where what kinds of points can appear? Yeah, it's like the points, IP. So I'll just write that. Pins, are the only places where IPs can appear. Again, can appear, not must appear. It's not must, it's can. Okay. So as you can see, pins are very much analogous to CNs, except that we analyze F double prime instead of F prime. And the purpose is to try to locate IPs as opposed to local maximum points. Right. But these are very much analogous. And the procedures are very similar. Okay, so if you get the rhythm for this field here, you'll get the rhythm for that field there. Okay. say using that analogy. Just like f prime somewhere tells you nothing about what f itself is there. Okay, likewise, f double prime does not tell you what's going on with f prime there, what it is in value. On an interval, it can describe its behavior, right? But not at a particular point. So be very careful. Okay, make sure that you know which relationships apply, which relationships don't necessarily apply. All right, now in my notes, I don't have time for this example. In my notes, what I do is I find the inflection point for the guy we did last time. Remember that guy we did at the end of last time? Not the trig guy, but the polynomial, the cubic, right? So in my notes, I find an IP. But I'm going to do that from scratch on a later problem, so I don't want to waste your time with that. It is in the notes. I'm going to go straight to the second derivative test. All right, so before we go to our actual example, I'm going to do the second derivative test. Okay. Part C, second derivative test. Now, what is this? Well, it's an alternative to the first derivative test. So really, the aim of the second derivative test is the same as the aim for the first derivative test. All right, it's an alternative. It's an alternative to the first derivative test. Okay, for doing what? Well, what did we use the first derivative test for? We were classifying a point at a critical number as a what, or what? As a local max point, a local min point, or what could it be? It could be neither, right? Alternative to the first DT for what purpose? For classifying a point, a physical point on the graph, okay? At a critical number, a Cn, as a, all right, well, as a local max point, a local min point, or neither. However, the second derivative test, although when it can work beautifully. One bad thing about the second derivative test is that it cannot identify a neither point. Okay, so we cannot identify this kind of guy by using the second derivative test. To find this kind of guy, you would need either the first derivative test or some other analysis. All right. So the second derivative test can only be used to find local max points and local min points, if that. All right. But the same overall purpose is the same. And the thing is, the second derivative test, like I just said, and we see this sometimes in calculus, in math, sometimes when it works very quickly and very beautifully. All right? But unfortunately, there are other times when it's not so hot, and in fact it doesn't give us a conclusion. All right, take a conclusion. All right. Okay, question. Okay, any question? Any question? All right. Let's assume C is a Cn where specifically f prime of C is 0. Okay, so we're going to assume that C is a critical number. We need the derivative there to be 0. Okay, which means we have what kind of tangent line? Yeah, horizontal tangent line. So the tangent line is horizontal. Okay. And by the way, why do we need this condition? And I did mention this before. It is a handy rule of thumb. Okay, remember that if you consider f, f prime, f double prime, f triple prime, and so forth, at C or A or whatever, okay? As soon as one guy goes D and E, what happens? All higher order derivatives will also be D and E. Okay? So it's like dominant. As soon as one guy goes D and E, the rest of the sequence goes D and E. All right? So in particular, comment here. If f prime at C does not exist, what do we know? F double prime at C also does not exist. And by the way, the second derivative test is not happy when the second derivative is undefined, as you might suspect. So if f prime is D and E there at the critical number, the second derivative test says, no, I'm not going there, no. Because I know your second derivative is messed up, I'm not dealing with that. All right. All right. So we have a critical number. it's somewhere where f prime is 0. I mean, you know how it normally goes, right? We set f prime of x equal to 0, we solve, we get the zeros, right? Make sure they're in the domain. Okay, yeah. Now the question becomes, so at this critical number c, what then is the second derivative? And what do you think is the only thing I care about, the second derivative at c? Not its value so much, but its sign. Just like before, right? It was the sign of that prime we were concerned about, not so much the actual values. Same thing here, we're concerned about the sign. All right, so what's f double prime of c? And again, just like with the first dt, I'm doing this by picture. Okay. So what's f double prime of c? All right, what is the second derivative at this critical number? Remember, we only apply this to critical numbers, right? The point being to classify local extrema. All right. First of all, what if the second derivative is negative? What if the second derivative is negative? All right. Okay, so here's the deal. Okay, if the second derivative is negative, all right. And by the way, there are other assumptions, but those are for freaky cases. Let's not worry about that. Okay, bottom line, okay, for unfreaky cases. If the second derivative is negative, okay, let's think about this. That means that the graph of f is what? Concave down, all right? And remember, the first derivative is 0, all right? So that means we have a horizontal tangent line, all right? The fact that f prime is even defined, that means that Big Daddy f had to be defined, right? Okay, so there's a point there. The first derivative is 0, that means we have a horizontal tangent line. The second derivative is negative, that means that we have concave down. So it's got to go like this. All right? So again, draw the picture. All right? If the second derivative is negative, that means that the f graph is concave down. That means this point is a local max point. Okay, that means that we have a local maximum point at c. How do I get the y coordinate? Plug it to Big Daddy f, f of c. Yeah. But I need you to be careful here. Local max point. Okay? Word association goes bye-bye. The word association fails here. I have to warn you about that. So when you think the second derivative is negative, you think concavity. Again, if the second derivative is negative, it's concave what? It is concave down. Draw the picture. Okay. Now you might think negative down. Oh, I'm thinking min. No, it's max. So here's the case. Here's the place where the word association fails. It's a local max point. The way to remember that: think concavity. Okay, think concavity, and then you realize it's a local max point. Right. Okay. Question.
So what does that symbol say next to f graph?
CD. Concave down.
Oh, okay.
By the way, technically, I think we should assume f double prime is continuous, but not going to mess with it. Don't worry about the freaky cases. All right. Now, case 2. All right. What if the second derivative is positive at c at our critical number? All right. Well, okay. First of all, if the first derivative is even defined, that means Big Daddy f is defined. There is a point at c. Because we assume f prime is 0, we have what kind of tangent line? Horizontal. All right. Now, the second derivative is positive. That means that the f graph is what? Concave up. Goes like this. What kind of point do we have here? We have a local midpoint. All right. We have a local midpoint at c f of c. All right. Again, it's a local midpoint. This fails the word association, but it is what we get. Concave up. We have a local midpoint. But again, be careful. That's where the word association fails. All right. Questions?
That horizontal line is just to represent FC, right?
The horizontal line indicates that we have a horizontal tangent line.
Okay.
Okay, which means that because again, the only way, we're the only place where we can have local extrema at critical numbers, right? That means that the first derivative is either 0 or d any. Because means you can go up this way, right, and down that way. So, yeah. That's why we need the derivative to either be 0 or undefined.
Okay.
Okay. Now, you might ask, well, why don't we like it? Why don't we like f prime to be d and e? Because the problem is f double prime becomes d and e. Okay. Okay. So, big case 3. What if the second derivative is either 0? We haven't talked about that yet. What if it's 0 or d and e? Okay. You know what? If this happens, you know what it tells us? It tells us jack. It's not the official term, but the second derivative is inconclusive. So the official word is the second derivative test is inconclusive. All right, second derivative test is inconclusive, meaning you've basically wasted your time. Although on the exam, I might ask you to apply the second derivative test. Maybe the answer is, well, the test is inconclusive. All right. But the bottom line is we don't know. It could be a local max point, local min point, or neither. We don't know. Okay. Which means that you might have to use what test? First derivative test. Or look carefully at the algebra trig or do something. All right. Consider the range, whatever. All right. So like I said, if you see that f prime is d and e at the critical number, you know f double prime is d and e. There's no point in doing the second dt. You know it's going to be inconclusive. Okay, there's no point in doing it. All right. So, well, that's easy, inconclusive. Then we have to do something else. All right. Now, I wanted to give you some examples of this. All right. How come it's inconclusive? Well, I'll give you a set of examples. Okay, I'm going to show you various situations. Okay, so here's some examples where f prime at 0, let's say, is 0. Okay, and f double prime of 0 is also 0. Okay, but we're going to get different kinds of points. Okay, so I'm going to give you 3 examples of a function f where both the first and second derivatives are 0. Okay, and we're going to see why we might get different results. Okay. By the way, the second dt is happy about this, right? The second dt is happy that the first derivative is 0. As it turns out, the second dt will be sad that the second derivative is 0. I'm drawing a lot of these smiley and frowny faces today. It's not how bored it's preschool, right? All right, that's okay. Calculus was fun in my preschool. All right. Okay, let's look at some examples. Okay, now, let's see now. Let's see. If I take a linear guy, that derivative is never 0. So let's go to a, let's see. For a quadratic, actually, the second derivative is always going to be non-zero. So we better start with third or fourth. Right. How about this? F of x equals x to the fourth. Okay? How do you graph y equals x to the fourth? Well, it's an upward fold. Technically, it's not a parabola, but it is an upward fold. All right. Looks like this. All right. By the way, very flat. Okay. This guy's flatter than y equals x squared is near the origin. Okay. That reflects the fact that we have these zeros here, right? Okay. So look what we have here. Okay. Yes, we do have a horizontal tangent line. Great. In this case here, we have a local what point? Local min point. Okay, or local minimum at x equals 0. All right. Can you think of a closely related function that's going to have a local max point there? Yeah, opposite of x to the fourth. Yeah. That looks like what? Well, opening downward, right? Looks like this. That's the graph of y equals the opposite of x to the fourth. And we have here a local max point. Okay? But this guy couldn't tell. See, if your second derivative is 0, you can have these different behaviors. Give me an example of a guy that has neither. We've talked about it before. F of x equals x cubed. Right, x cubed, x to the fifth. Again, not x to the first, because then this guy's different 0. But, okay, well, yeah, x to the third, x to the fifth, x to the seventh. F of x equals x to the third. Okay, that looks like a rising snake. Okay, if you work it out, you'll find that both the first and second derivatives are 0 and 0. All right, in this case, we have neither. examples demonstrate, right off the bat, this demonstrates that, that this cannot give us a conclusion, right? Because I'm giving you different examples where, the second derivative of x arrow is 0, and yet the point could be a local midpoint, could be a local max point, could be neither. All right. Questions? Questions? And same for TNE. Okay, same for TNE. You can imagine a vegan, like absolute values. Over here, maybe some other corner. Okay, question. Question, please. All right. So remember, think in cavity. That's the way to look at it. Think in cavity. All right. I think we're ready for some graphing. Right? Heavy-duty graphing. Any questions so far? We've been talking about principles for the first 40 minutes or so. We've been talking about principles. Ready for some graphing. Right? Actually, let's gather together our thoughts. Okay? Let's get a schematic going.